We now start upon an altogether new topic, and this is the issue of relating discrete time signals to continuous time signals. Suppose we have a continuous time signal like x t, x t. Is it possible to find a discrete sequence, time sequence x n, such that x n carries within itself all the required information about x t? Does there exist an x n which maintains all required information about x t? Now, what do we mean by saying all required information? That seems a pretty vague thing to say. It simply means that, well, if x n is given, can we obtain x t from it? If yes, then we can say that x n carries all information about x t. So, this is what you can call the proof of the pudding. If you can do this, then we can say that x n carries all the information. So, we want to go from a continuous time function to a discrete time sequence and see if all information about x t can be preserved. Now, the first step in this process is to convert it into a sequence of so called samples of x t, and in the second step of the process we will we will represent this sequence of samples of x t by the sequence x n. So, let us this entire discussion is going to be very graphics intensive. So, we will make a few plots to illustrate the idea. So, suppose this is time, continuous time, and we have some function x t that looks like this. X t. If x t looks like this, then the first thing we do is to sample x t. The way one samples x t is the following. Sampling of x t amounts to recording its value at certain instants of time certain instance of time only and neglecting the rest. So, you have to choose certain instance of time. We will choose what is called uniform sampling. Where the chosen instance of time are at uniform distances from each other. Now, the samples can be taken in the form of impulses whose weights are determined by the value of x t at that point of time. In short, what we would get after sampling would be a train of impulses. This train of impulses would be such that the strength of an impulse at a particular point n t s would be equal to the value of x t at that point of time. The sample train that represents excess of t, that represents x t, would be a train of impulses located at t equal to 0, t equal to T s, t equal to 2 T s, and so on. Of course, also at t equal to minus T s, minus 2 T s, and so on. T s is called the sampling time or sampling interval. There are several questions which we haven't even begun to answer. For example, what determines T s and so on. But first let us see what an impulse train is and how it is defined. The definition of an impulse train, which is essential to the continuation of the discussion. Of a Dirac impulse train it is a train of impulses uniformly spaced with respect to each other at a distance T s and all having the same magnitude. So, I will denote this by impulse train, Dirac impulse train dt, where dt equals summation over n for all n, that is to say n equals minus infinity to infinity, delta, where delta of course represents the Dirac delta, t minus n T s. This is dt. One of the first things we will require is to find the Fourier transform of dt. What is the continuous time Fourier transform of dt? Continuous time Fourier transform of dt. To find the continuous time Fourier transform of dt, first note that dt is a function of continuous time, and that is why we are looking for a continuous time Fourier transform of it. Second, it is a periodic signal because it is being defined like this, it is a periodic signal. Now, If we wish to find the continuous time Fourier transform of a periodic signal, which is not a finite energy signal but a finite power signal, we have to go through a certain set of steps. All this follows from the fact that it is not a finite energy signal. So, dt is a finite power signal. Dt is a finite power signal. So, in order to find its Fourier transform, the first step is to find its continuous time Fourier series coefficients, CTFS coefficients of dt. I will call them dk given by 1 by Ts integral say minus Ts by 2 to Ts by 2. You have dt e to the minus j 2 pi by Ts k t dt. This is what we have. Okay. What does this evaluate to? We have to recognize, let's substitute for dt in the expression. dk equals integral minus t by 2 Ts by 2 to Ts by 2 of course 1 by Ts times all this, and dt is a sequence of impulses delta t minus n Ts, okay, e to the j 2 pi by 2 pi k by Ts dt. This is what we have. Now, note that this is equal to 1 by Ts integral minus Ts by 2 to Ts by 2 of simply delta t e to the minus j 2 pi k by Ts I really think that there's a mistake over here. This should be n. All right, made that correction. Now 2 pi k by Ts dt. This is what we have. How is this manipulation justified? Simply because of this train of impulses delta t minus n Ts. Only one lies within the interval minus Ts by 2 to Ts by 2, and that one is delta of t. The others are outside the scope of the integration, and they are therefore not relevant to the integration. Now, in order to evaluate this integral, we have to simply apply the shifting property. And that gives us dk equals 1 by Ts for minus k less than minus infinity less than k less than infinity. So, it's all the discrete time Fourier series coefficients are equal to 1 by Ts. This is what we have. So, now we have the DTFS coefficients, sorry, CTFS coefficients, continuous time Fourier series coefficients, an infinite array of coefficient values. From here, how do we proceed to finding the continuous time Fourier transform? from the continuous time Fourier series, we want the continuous time Fourier transform. Remember that the Fourier series coefficients, each Fourier series coefficient gave rise to one impulse in the frequency domain representation of the periodic waveform. You will essentially have to recall our discussion in which we extended the scope of the continuous time Fourier transform to also encompass finite power signals such as dt. There we said that if you have delta omega as an impulse in the frequency domain, its inverse Fourier transform would be 1 by 2 pi. 1 by 2 pi had a Fourier transform of delta omega. Fine. So, what we have is that 1 has a Fourier transform of 2 pi delta omega. Fine. Hence, 1 by Ts will have a Fourier transform of 2 pi delta omega by Ts. So, this is what we get. The 2 pi delta omega by Ts is for this first coefficient. Now, what we have is a series of these coefficients at different frequencies k omega naught or k 2 pi by T naught, k 2 pi k omega naught, which is k 2 pi by Ts, and each of those is independently going to give us one expression like this. This one came out of d0. This is the result of just considering d0. Similarly, we have d minus 1, d plus 1 and so on and so forth, which gives us the complete Fourier series representation. And this therefore yields what I call d omega, which is the Fourier transform of dt as given by 2 pi by Ts summation over all k delta omega minus k omega s or k 2 pi by Ts. This is the complete transform of dt. So, let us keep this in mind, an important result. Now, we have the Fourier transform of the discrete time sequence of the discrete impulse of the impulse train in continuous time, and then the very important property of this you see is that even in the frequency domain it is an impulse train. So, this is one of the rare cases where you have a function whose Fourier transform looks somewhat similar to itself. How do we depict the Fourier transform, or how do we depict dt itself? This is dt. Fine. Now, what is the distance between one sample and the next? It is Ts, 2 Ts, 3 Ts, minus Ts and so on. This is the spacing, and the heights of the strengths of all the samples is unity. Now, let us look at d omega. This is the omega axis, omega axis, and what you have is d omega. Now d omega is also an impulse train, but what is the spacing between the impulses here? It is 2 pi by Ts. So you have over here an impulse at 2 pi by Ts, then you have at 4 pi by Ts, and so on, minus pi by minus 2 pi by Ts, and at each of these places you have impulses. What is the height of this? The height is also equal to 2 pi by Ts. Both these are called Coombe functions. So dt is a Coombe function, d omega is a Coombe function. These are both Coombe functions, and it is interesting, as I said, to see that the Fourier transform of the Coombe function is also a Coombe function with a slight difference in the values of along the horizontal and vertical axis. Otherwise, they are both Coombe functions. Coombe function goes to Coombe function. Okay. Now we have dt with us, and let us say we have xt. What we do is to multiply dt and xt to get xs of t. This is called the sampling, the act of sampling, or this process of sampling. The process of sampling is to carry out this product xt dt. When you do xt dt, let us make a sketch for it. Let us say this is xt. Now xt dt is to take this dt sequence that we have over here and multiply it with this to get an impulse train which is xt dt. So dt is already given, it is all of uniform height equal to unity, but because of multiplication by xt, the strengths of the impulses will change at different places. So you will get something like you have a train of impulses of heights determined by the then value, by the current value of the xt, the function xt, and this xt dt is what we will call x s of t. That is what we have plotted over here. Xt is this xt is this function, and x s of t is this, all these impulses. X s of t is all these impulses. So we now have x s of t. Let us just first try to find the Fourier transform of x s of t. Before we can find it, we should assume some kind of a spectrum for x of t. So let us say that x t transforms to x omega. Let us say x t transforms to x omega, and x t is this original black curve we have over here. If you transform it to x omega, you will get the Fourier spectrum, the magnitude spectrum, let us put it as, which let us say for simplicity's sake looks like this. The highest frequency value at which x omega is non-zero we will call as b, and at the other extreme we will call it as minus b. So, we are assured, of course, we are making an assumption that xt is real, otherwise we would not have had a symmetric spectrum, but in any case the point is that it has a bandwidth from minus b to b. So, let x t have a bandwidth running from minus t minus b to b. If we have this, then let us look at the expression for excess of omega. Excess of omega is the Fourier transform of a product. It is the product, that is, it is the Fourier transform of xt convolved linearly with dt. Okay, but because it is a linear convolution, what we are going to get is in the frequency domain. Sorry, it is not convolved, it is multiplied over here. It is multiplied over here, and hence the Fourier transform will be a convolution of the Fourier spectrum of dt and the Fourier spectrum of xt. What you will get is 1 by 2 pi d omega convolved with x omega. Now, what is d omega? We made a plot over here of d omega. D omega is this is d omega. You have d omega and you convolve it with x omega. Convolution of an impulse sequence with x omega with the Fourier transform of any continuous signal will yield a series of copies of the original signal. In short, you will get something that looks like this. Xs of omega this is excess of omega, and how it is obtained is by a convolution of the impulse train d omega containing impulses over all these places and the x omega x omega is just this simple one time function. When you convolve the x omega with d omega, this is what you will get. You will get excess of omega as shown over there. Fine. This process of generating excess of omega is called the ideal sampling process. Let us now evolve an expression for excess of omega. First, what is excess of t? Excess of t equals x of t multiplied by d of t. Hence, excess of omega must be equal to 1 by 2 pi times x omega convolved with d omega. Let's go back and find out what is d omega. Now, d omega is equal to 2 pi by Ts summation over all k delta omega minus 2 pi by Ts times k. For convenience, let us call 2 pi by Ts as omega s in future. Okay. So, this is d of omega, and we of course have x omega. Now, when you convolve these two using these delta functions over here, at the location of each Dirac delta in the frequency domain, what we will actually get is a copy of x omega translated to the position k omega s. So, you get that x s of omega equals 1 by 2 pi d omega convolved with x omega equals 1 by 2 pi times 2 pi by Ts multiplied by the summation over all k of x omega minus k omega s. This is what we get. So, 2 pi cancels the 2 pi in the numerator, and we finally get x s of t, which is equal to the sample train over all n of x n Ts delta t minus n Ts. This is excess of t having a transform of 1 by Ts summation x of omega minus k omega s. The sketch of this was already shown in the previous slide over here. This is the sketch. It has a constant repetition of these copies of x omega, where x omega's original is shown over here. All right. Now that we have excess of omega, let us see if it is possible. Excess of omega is the Fourier transform of excess of t. So, if we have the sample train alone, then we are already one step towards generating the discrete sequence xn, which carries our information or which represents the information about x of t. So, from excess of nt we will define the discrete sequence the discrete time sequence x n equal to excess at n Ts. This is what we are going to do. So, having done this, this is the only thing we will carry with us, the discrete sequence xn. Suppose we have the discrete sequence xn, it is not hard to reintroduce excess of nts, that is, it is not hard to get excess of t. How do we get excess of t given xn? Simply as follows: excess of t equals summation over all n x n delta t minus n ts. This gives you excess of t back. So, this much is straightforward. If you have excess of t, you can go to xn, and then with the knowledge of ts, of course, with the knowledge of what value ts takes, you can get excess of t back. If you did not have the knowledge of what ts is, then of course you would have a problem of not knowing what is the space between the consecutive samples in excess of t. But suppose you know ts and you know xn, then you can get excess of t. Thus, the real challenge is how to get xt back from xs of t. That is the real hard question. How do we do this? If we go back and take a look at the Fourier spectrum of xs of omega, it does give us some hints on how to do it. You see, this has a spectrum identical to x omega, except for a scale of, if this was equal to 1, then this has a scale of 1 by ts. We know this. But apart from this matter of scale, which is not a serious matter, the shape of excess of omega in the neighborhood of omega equal to 0 is pretty much identical, except for the scale factor, to x of omega. So, one way to get something back, to get back x omega from excess of omega, is to just get rid of these other copies that have arisen on all sides. These copies are called aliases. They are duplicates, photocopies if you like, of the original x omega. So, you want to get rid of all the aliases except this, which is called the central alias. You only want to capture the central alias and get rid of the others, and evidently that is not very hard to do. All you have to do is to set up an ideal low pass filter. An ideal low pass filter is one which allows all frequencies up to a certain lower than a certain frequency and rejects everything outside. So, now you see, this is after all omega s, this is 2 omega s, 2 omega s, this is minus omega s, and so on, and we really need a low pass filter such as this, to be imposed. This low pass filter I will call as L of omega. Now, what should be the bandwidth, what should be the cutoff frequency of this low pass filter? L omega must have a cutoff frequency of omega s by 2, right. It should have a cutoff frequency of omega s by 2. If you have a cutoff frequency of omega s by 2, then applying L of omega to excess of omega would imply multiplying the two Fourier transforms, and this process would yield only the central alias. Now, you can even make sure that the scale error in the scale of 1 by Ts is cancelled off by giving an appropriate gain of Ts to L of omega. So, let us define L omega properly. L omega must be equal to Ts for mod omega less than omega s by 2, and it must be equal to 0 mod omega greater equal than or equal to omega s by 2. This is what constitutes the specification of L omega. Now, let us see what happens theoretically, at least for the figure that we have shown over there. What should happen is x s of omega gets multiplied by L omega, and therefore, this equals 1 by T s summation over all k delta x omega minus k omega s times L omega, which by the fact that it has a cutoff at omega s by 2 will simply give you x omega. This means we have successfully gone through the entire sequence of steps. Starting with xt, we got xs of t, from which we got xn, from which with a knowledge of Ts you can again get xs of t, and using L omega we got xt again. So, it all seems to be working fine. That we can start with a continuous time function, get xs of t, then represent it by xn, a discrete time sequence, and from the discrete time sequence and with a knowledge of the sampling time, the sampling period interval of xs, we can recover xst from xn, and from xs of t, by doing what we just did, ideal low pass filtering, we can get xt. But there are some catches in this whole thing. The catch arises from the fact that we have not ensured by any overt statement that xt must maintain certain standards in order to be represented in this manner. Let us go back to the sketch of the Fourier transform of xs of omega. This is what we had as xs of omega, and this resulted from the fact that omega s was equal to this much. But suppose omega s was less than this. Suppose omega s, suppose we had choose Ts dash equal to 2 Ts, so that omega s dash becomes equal to omega s by 2. Supposing we did this, then I will plot it on the same axis for convenience. We would get this as omega s dash, exactly half of this omega s dash, this would be minus omega s dash, and the first alias would of course remain the same, but since Ts dash is 2 times Ts, we would also get half the height. So, let us do that. You would get half the height. So, you would get half the height. Now, apart from getting half the height, there are other things which happen. Since this is omega s dash, the second alias, the original or central alias is what we have just drawn. The second alias would not be so close, would not be where the previous alias was, but it would be centered about omega s dash. So, you would get the second alias like this, the third alias like this, the third alias would be like this, and so on. On the left side you would get the second alias like this, third alias like this, Now you see that the aliases are overlapping, and if we can just redraw this part over here for separately, you get an alias like this, a second alias like this, a third alias like this. Now the central alias that was there earlier is still there, though it is scaled by a different amount. Scaling is not an issue here. The serious issue is the fact that while there we realized that eliminating the non-central aliases, the second and higher aliases on the left and the right side would yield or would allow to remain behind only the central alias, and we could reject them earlier because they were sufficiently far away from the central alias. So, you could place a low pass filter which discriminated the central alias from the remaining aliases. Now, we can't do it because they are overlapping, and hence there does not exist for a sampling period of Ts dash, there does not exist a low pass filter L omega that can reject the non-central aliases completely. Clearly, this has happened because we chose Ts too large. So, Ts should not be very large, rather we chose Ts dash too large, and therefore, it is important that the sampling time or the sampling period not be too large. From a time domain point of view, this simply says that the longer the time interval, the more scope the signal has to make changes in itself, and therefore, a sufficiently short time sampling time interval is required to track all possible changes of the signal from one sampling instant to the next. So, because of this problem that we have faced here, we conclude that only if Ts is small enough that is to say, only if omega s is large enough will recovery of x omega from excess be possible. Sorry, excess is not right. From excess of omega be possible. Okay, only when it is large enough will the recovery be possible. So, how much is large enough? Of omega s is large enough. This is clear from the figure. Omega s must be at least equal to twice the bandwidth of the signal x omega. If x omega equals 0 for mod omega greater than equal to b, then we see that omega s must be at least 2b. If it is at least 2b, then at least theoretically an ideal low pass filter will be able to extract x omega from x of s. This constraint on Ts equal to 2 pi by omega s imposed by the bandwidth b of xt is called the sampling theorem. Is called the sampling theorem. Thus, we finally get that omega s must be greater than 2 times b, that is to say 2 pi by Ts must be greater than 2b, so that Ts must be less than 2 pi by 2b, that is pi by b. This is the sampling theorem. As long as the sampling theorem is followed, that is, as long as Ts is chosen to be no larger than pi by b, which clearly means that the greater the value of b, the smaller should be the value of Ts. The greater the value of b simply means that xt has higher and higher frequency components. That means that it is capable of very rapid variation, and as xt varies more and more rapidly, to capture all its movements one requires a smaller and smaller Ts, that is, it has to be sampled more and more frequently in time. So, we conclude that with ideal sampling, ideal impulse train sampling dt sampling and an ideal low pass filter of bandwidth equal to b, it is possible a bandwidth equal to b and gain 1 by gain of Ts it is possible to retrieve x t. It is possible to retrieve x t exactly. But then this is just half the story, rather less than half in fact. There are so many problems with ideal sampling